Triv, I challenge you to a duel. I have a huge pencil.
I have a huge pen.
On guard!
Chemistry.
Module 1, no, 2.
Two, and hydrogen?
Hydrogen bonding, that's it.
Okay.
Right.
So I mentioned before, chlorine name, about hydrogen.
Yeah. Stronger than the van der Waals and the dipoles, which we mentioned at the end of part 2.
Yeah, it's 50, van der Waals is 1, dipoles is 10.
Relative strength, yeah.
And this gives stuff that have it, well, harder to boil.
Yeah.
Higher boiling points.
So, H2O.
Yeah, so it's H2O and NH3.
So basically stuff that has a lone pair and hydrogen.
Yeah.
That's how it works.
Yeah, I'll draw it up.
Yeah, water's the one you really need to know.
Yeah.
You have to be able to apply it to nitrogen if you need to, but...
Yeah, it works by the lone pair being extra negative, hydrogen being a bit positive. So there's a little dashing line here. It's dashing. And that's the hydrogen bond.
Because this is slightly negative compared to this, which is slightly positive.
Yep, and that's how it works, and that's how you draw it in the exam. You might draw a few, and if you keep drawing this, you can already actually see that it makes water a strange shape.
Yes, if you think of most other things, in fact all the other things that don't have hydrogen bonding, if you make a solid of something and then put it in a liquid of the same thing,
it will sink.
It will sink, because that's what a solid is, isn't it? It's all condensed, it's all ordered.
But like icebergs float on water.
And the water in your cold drink in the summer,
to
the top.
Floats to the top. Because it makes basically holes where air goes in when it
spaces
freezes.
it out when it's ordered.
Which is strange.
Yeah.
Also it's tiny, but boils at 100 degrees.
Similar sized things would boil at about -20 to -73.
Yeah, a lot colder.
This boils at 100 degrees, that's a lot more.
It is a lot more.
And it's because of these.
It is, the hydrogen bonds, they make a much higher boiling point because they're more energy to break. And they're quite important in lots of places.
Yes,
DNA, yeah, they make the
enzymes,
shapes,
proteins.
all of that.
Should note, this is quite strong compared to dipole and van der Waals, but this is still the strongest.
Much stronger, because this is a covalent bond there, and that's a lot stronger.
Yes, so don't get tripped up, it's not that makes water so good, it's just that's a major thing.
Yeah.
Covalent is the
When you're boiling stuff, you're not splitting that bond, you're splitting that bond.
Yes, that's right. And that's hydrogen bonding, we said we'd go on to it in part 3. There it was.
There it is.
So we should go on to metallic bonds. So
metallic bonding.
Yeah. So should be quite familiar from GCSE.
Yeah.
Not much development really.
Yeah, bonds between metals.
Yep.
And well, we'll probably draw it.
Okay.
Yeah.
If we'll go for a group 1 metal, something like lithium.
Lithium, yeah, I say lithium.
Lithium. Reason being, all the ions will just be a plus like that, and every one of these would give off 1 electron.
Yep. And this would be, I was going to do it in blue.
Oh yeah, you can do the electrons in blue just to. And there'd be a few layers of this. I'm only going to draw 2. This would keep going.
And these would just be randomly about. And if you label this up,
these
are positive ions, not protons.
Positive ions, and these are delocalized electrons.
Yeah, you actually call this a sea of delocalized electrons.
Because there'd be lots of them. I chose lithium because, like I said, each 1 positive ion will give off 1 delocalized electron. With magnesium, for every 1 of these, 2 electrons will be given off, and for aluminium, 3. So that's why I used this example.
Yeah.
These are free to move around.
Yeah.
That's why they're delocalized. They can move.
They can jig about, and that means metal can do a few things.
Yes.
Like conduct electricity.
Yep. Because these are free moving, you can put a charge across it, make them move in a particular direction.
Yes.
They're malleable and they're ductile.
Yeah, these 2 words you need to know. Ductile means you can draw them out to strips.
And malleable means you can hammer them into shapes. And that's because the way it's layered, you can stretch them. It sort of stretches them out, and they fold into each other and make a straighter chain.
Yeah, that sort of thing.
Sort of that. So
also
not that hard.
Quite high melting point than that.
Yeah, because these move around, it means quite a lot of energy to break them. Because if they stay still, you'd just be breaking a bond, but the bond moves essentially. Yeah. And makes lots of bonds at the same time, and it gives them high melting points basically.
Yeah.
And that's metals.
They're
not that hard.
No, you just need to be able to draw that and explain it basically.
The words malleable and ductile, don't get them mixed up. You need to remember which ones.
No, you need to remember them, and you have to compare them with covalent and ionic. So let's go on to that.
Let's do that now.
All right. So ionic and covalent.
Yep. Sort of touched on them earlier, but this is more about the structure than what they are.
Yeah. So I think we should do both at once.
We can do both at once.
Let's split up the board.
Okay. That side's covalent, this side's ionic, so I'll put the title ionic.
Alright, I'll put the title covalent.
Do ionic first, I think.
Yeah, makes sense.
Ionic is the electrostatic attraction between oppositely charged particles.
Yeah, mentioned before.
In a solid, they're neatly arranged like this. Again, it would go on a lot more.
Got a lot more.
So this might be positive,
Positive would be negative, positive, negative is pretty much how it works. That'd be negative, negative and positive. Yeah, it sort of makes a lattice.
Yes, an ionic lattice. And they have high boiling points because you've
They
got
do.
to break all
All
of the
those bonds.
electrostatic attraction.
Which there's lots of.
Thing you must know about ionic that can be quite tricky, this as a solid doesn't conduct electricity. There's
No.
nothing free moving.
There's nothing free moving at all. But,
If you put them in a
put
beaker,
them in water,
they
then they split. And that means they sort of act as the circuit.
Yeah.
If you had electrolysis, your positive one goes to negative side. You know,
So
make a circuit.
when molten, as it's called,
Yeah.
they can conduct because the things are free moving. All ionic stuff does dissolve in water.
Yeah.
And that's pretty much ionic summed up.
That is pretty much how it summed up. Covalent. That's it's different.
You can have simple covalent and the bigger covalent, the proper covalent lattices.
Yeah. So simple covalence.
Stuff like hydrogen,
Yeah.
stuff like that, Cl2, all the little things.
All the little things like
basically.
this. They're not bonded in like a lattice. They're sort of.
They're just
they
to
call
each other, really.
Yeah, they just call it. That's why they call it simple.
Yeah. And these have very low melting points because
Yeah.
you only need to break that bond. That's
well,
it, really.
yeah. The bond between the two hydrogens is quite strong, but the bonds between the hydrogens next to the hydrogens and whatever
Isn't
really
very
weak.
strong, yeah.
Yeah.
So that's simple, but you then get the giant
Yeah, you
covalent
get the
lattices.
giant, and they're stuff like well, it's mostly to do with carbon.
Yeah, you can have graphite, diamond. You should be familiar with Buckminster fullerene.
Yeah.
We don't really touch on that here anymore.
No, but
And silicon oxide is one you must know.
yeah. And these are much bigger. So if you draw, I'll roughly draw what diamond looks like. Diamond's sort of loads of carbons with every single bond attached to.
Yeah, so
Or
at the top it
carbons.
has a little point, then that's bonded to 4 in a tetrahedral. Then
Yeah.
each of those is bonded to 4 in a tetrahedral.
And this goes
And
on.
then it goes back in to make a sharp point at the bottom.
Yeah.
That means there's nothing free moving in it, which means that
At all, so-
it doesn't conduct
No.
electricity. However,
There's it is as well.
because of all these strong bonds connected to lots of strong bonds, it's a very hard thing to break.
Yeah, very hard for them to break. It does. It's not malleable. It's not ductile. It's just strong.
It's very strong. Compare that to graphite.
That's a bit different. Now they've got quite strong bonds in the sort of layers where they are here, but they're in layers, and the layers can slide, and that makes it quite soft. That's why you write it with a pencil. It's actually sliding off. Yeah,
In terms of actually breaking each layer, it's pretty much as hard as the diamond, but
breaking things
because
between the layers.
the gap is between it isn't very
Yeah.
strong at all.
So I've got a bit here.
It's soft.
That bit's really easy to move.
It also has delocalized electrons in
In
between,
between the
the
layers, which means conducts electricity.
Conducts electricity. Yeah. SiO2, silicon oxide. That sort of conducts electricity. You don't need to know much about it.
No, but
It's
it's
fairly good, but it's a semiconductor. is what it makes.
Semiconductor, yeah.
You don't need to know much about it. You just need to appreciate that that's a giant.
Yeah.
These are giant. These are the simple ones. And these are really high boiling points. These are really low. No, these are really high.
Yeah,
these are really low.
Yeah.
You need to know all about covalent and ionic, basically.
Yeah, and that's pretty much it.
Yeah. Let's go sum up part 1, part 2 and part 3.
Alright, let's do it. So, summary time.
Yep, this was module 2 of unit 1, F321.
It was quite a big one, split into 3 parts.
Yep, so in part 1 we started off with evidence for shells.
Yeah. 3 points that make it different. So, Evidence shells all about ionisation energy, and there's points that affect that.
Yep, so shielding, nuclear attraction, atomic radius.
Repulsion. And how that produces shells, because it becomes loads of energy really suddenly when you go past a point which would be changing a shell.
Yep, and it
That's
also
shielding.
provides evidence for how many electrons are in each shell.
Yeah, it does.
Then we went on to orbitals, which were
Yeah.
new above GCSE,
So,
S, P, D and F.
Yeah, I can't remember them. And there's 2 electrons per orbital, and the opposing spins.
There's a lot of definitions in this chapter.
There's hundreds to learn them.
I got onto subshells and the actual how to do it with the periodic table.
Yeah.
And we drew out a few examples of an ion, a normal atom, an atom that stops halfway through, so the drawing of the orbitals.
The order you have to do it in.
All that sort of stuff.
All that jazz.
After subshells, what did we go on to? I'm trying to think. This is quite a while ago now.
It was.
It's like half an hour ago.
Something like that, yeah.
We've had a cup of tea since then.
And a biscuit.
Did we go on to bonding after that? I think we might have done.
Yeah, was it like ionic bonding? And
Yeah.
I think it must have been.
Yeah, so ionic then went on to covalent. And you should know about them, the electrostatic attraction and the shared pair.
Yeah.
They
went on to
electronegativity and polarity, which leads into dipole to dipole and van der Waals.
Yeah.
Which led into hydrogen, which is now part 3.
It
which
is.
we've done in this video.
Hydrogen bonding and how it works between the hydrogen and the lone pair.
Yep. After hydrogen bonding we did metallic, which is the third of it, the type of big ones if you like.
Yeah, and how it conducts electricity, why.
The structure of ionic and covalent to finish that off.
Yeah, and when ionic conducts electricity and why, and
Yeah.
when the other one doesn't.
I have a big pencil.
I have a pen.
He's been James Trivett.
He's been Wayne Lack, Bib and Clever Cracker Squared.
If you have any questions, find us on Facebook or put it in the comments below.
Blue.
Easier on Facebook.
Easy.